on the right. Okay, yep, we're good.
Good.
Okay. And then, if everything else is ready, yeah, we should look at the
Hi, this is Jianping. Can you hear me?
Yes, we can.
Okay, great.
And Jianping, I think we'll just ask you, or when you're giving your presentation, just hit next and we'll advance the slide for you.
Okay, thank you.
Cool.
So we're still on the time or some delay?
I think, yeah, I think we'll start pretty close to the time.
Okay, great.
People are kind of trickling back from lunch right now.
Okay, that must be fun.
So the other conditions, I encourage you to correct the woman that might live in Austin, actually people will leave and choose it. Take how much you know, usually a lot of work, but then it's really good. I guess if we just shorten the discussion a little bit, me too. I also like how they cut the where we say here we do that and that and that and that. So maybe we're just gonna cut that. Oh. Yeah, totally confusing.
What the heck is this? Yeah.
Okay, let's get started. So my name is Lei Hu. I'm from NOAA Global Monitoring Laboratory. I'm going to co-moderate this session with Clayton Alder, who's from NASA JPL. So we have 9 exciting talks. And the first talk is given by Jian-Ping Mao from University of Maryland and the NASA Alder. He's going to present towards accurately measuring atmospheric CO2 enhancements from wildfires. Go ahead, Jian-Ping.
Thank you. This presentation is about measuring CO2 enhancement from wildfires using Goddard CO2 LiDAR. We have been developing this LiDAR for over a decade, had several airborne demonstrations. It's been great teamwork, and we are very thankful to support from Above and Ascend projects, ASTO, and Airborne Science Program. Next, please. We had this wildfire case totally by chance in the 2017 Airborne Science Campaign in Alaska. And recently we finished data analysis and published it. To our knowledge, this is the first use of LiDAR to remotely sense CO2 enhancements from large wildfires. And we also use the measurement to validate estimate of CO2 emissions from wildfires from the emission database and try to improve the estimate of carbon fluxes from wildfires. As you know, the measuring through the dense smoke plumes is very, very challenging for passive approaches, but it's an advantage for LiDAR, and we can do that accurately. Next, please. So this is a case we saw from the inside of DC aircraft over Vancouver Island on the return flight from this campaign from Alaska to California, and look at the northeast direction. And that's what we saw, the dense smoke plumes from the Canadian Rockies is on the left side. And the right side, you can see that this is the MODIS map of 5 thermal anomalies indicating the smoke plumes and the fire locations. Next, please. Left side shows the ground tracks of this return flight from Fairbanks to the Palmdale, California on that day. And I would like to bring your attention to the spirals. We had a total 8 spirals on this flight marked by circles. And between the 2 orange circles, that's Vancouver Island. So before that, we had 1 spiral over Pacific Ocean. And after that, we had a spiral for the at the Moses Lake in central Washington state. So spirals are used for measurement validation. And if you look at the right side, is a 3D view, let alone and from altitude of the in situ single point CO2 measurement at the flight altitude. And if you look at the second between the 2 spirals of Pacific and Moses Lake, the enhancement at the flight altitude, not too outstanding compared to the before that second, after segment, and those CO2 were even higher than that segment. So you could miss that what's going on underneath of aircraft from the in situ single point measurement. Next, please. So here the map of the LiDAR X CO2 retrievals for along the ground track of the return flight. And you can see here the enhancement over Vancouver Island were very evident before that and after that. XCO2 all pretty low. And the British Columbia wildfires is marked to the north of the segment. And also you can see that the high XCO2 over Nevada and California desert due to the little surface uptake on that in the summertime. Next, please. So here the time series of the LiDAR XCO2 retrieval in red dots. The enhancement segment is circled here. And also background is the LiDAR backscatter profiles. You can see the high return from surface and also significant returns from the smoke plumes. And the white line indicates the flight altitude, and the two spirals before and after the enhancement segment. And bottom is a histogram of the XCO2 retrieval for this about 25-30 minutes long segment, and in distance about 360 kilometers, so pretty large scale. The medial LiDAR XCO2 was about 406, and the background in situ XCO2 is about 402. So we estimated the enhancement, the average was about 4 ppm. Next, please. So we had a validation spiral soon after the enhancement segment in the central Washington state. So the comparison between the in situ and the retrievals, we had bias, very small bias, about 1/10 ppm, and the standard deviation is about 1 ppm for the 1 second average data. And here is actually total average for a few hundred data points retrievals. So compared to this measurement uncertainty, this 4 ppm enhancement is very, very significant. Next, please. So we try to use the data to estimate or evaluate the CO2 emission database, like a GFET and a QFET. So this is the simulation from the Goddard's Global Chemistry Transport Model, PCTM, for that day, around that flight time for the same column from like 9 kilometers to the surface, basically representing the tropospheric column. And this model uses GFET for the fire emissions. And the total release from the fire was 837 gigagram carbon on that day. And you can see the enhancement over Vancouver Island, near Vancouver Island, is not that much. It's about 1 to 2 ppm, not as much as we measured 4 ppm. So based on that,
sorry to interrupt. You have about 1 minute left.
Okay, so based on that, we suggest the GFET was clearly underestimated the emission. Okay, next one, please. So this is a simulation from another model, GEOS GCM Lowfield used for the simulation of all CO2 retrievals. And from this one also, you don't see much enhancement either, even weaker enhancement or near Vancouver Island, probably due to the an adjustment for the missing terrestrial sink in the model. Next, please. So the further investigation I needed, probably use the original model. We think is the better way, like an example for like an NU Wolf Castle model to study that and evaluate the CO2 emissions in the current inventory. And we also hope in the future, we have an airborne campaign plan targeting a large forest fire for this purpose. Thank you. I'll stop here.
we'll take one quick question if you have something urgent. Abhishek?
Can you ask Jensen what the uncertainty on the retrievals are? So he talked about just the RMS, which is the random component, but are there any systematic biases in the LiDAR retrievals that they observed and how that would impact?
Yeah.
your results?
Okay, I heard you, Abhishek. If you go to, can you go back to the slide?
Uh,
Yeah, the
we're-
validation
we're
slide.
kinda- We're running out of time a little bit, but
Okay, so I can just tell you that the bias average during that spiral down validation was the 0.1 ppm, and the standard deviation is 1 ppm. So compared to that, the 4 ppm enhancement is very significant.
Okay, great. Thanks, Jim.
Thanks, Jianping. Our
Thank you.
second-
Okay.
We'll move to the second talk. Our second speaker is Clayton Alder. He's going to talk about remote sensing of methane emission hotspots and their relationships to permafrost salts, vegetation, fire, and beaver activity.
thank you, Lei. Yeah, I'm gonna give a quick highlight here, try to go pretty quickly. If you're not very familiar with the methodology here, I'm gonna kind of glaze over some of that stuff. But please come find me later. I also have a poster that goes into more detail about a lot of this work. And also I'm gonna save a few of these topics for some of my colleagues who are presenting after me in this session. But really what we're doing is using the AVIRIS NextGen, which is a hyperspectral sensor. We're using a portion of the wavelengths that it observes to measure methane enhancements between the sensor and the ground. And so we're looking at reflected backscatter and seeing an absorption caused by methane in between the ground and the air. On the right there is what our data or what our methane retrieval looks like in raster data in the grayscale. And within that noisy data, we're looking for bright spots, which indicate greater concentrations of methane in between the air and the sensor. And then the rightmost RGB panels are kind of a zoomed in view demonstrating the high spatial resolution that we're able to achieve with this sensor, which is kind of a scaling breakthrough when it comes to detection of methane emissions. And I should say that we're really only sensitive to the highest level of emissions that you might expect in northern ecosystems. But the fact that we've now covered such a huge area allows us to think about statistics and determining kind of emergent patterns. So some quick stats. We've deployed this method in 2017, 2018, and 2019. We've imaged 170,000 square kilometers. That includes some overlapping areas. But what that gives us is 6.6 billion individual methane measurements to then go and relate to a plethora of other environmental variables at a cascade of spatial scales. And so this figure right here is showing an approach that we're taking with the data relating hotspot counts to mapped regions of prevalent thermal karst. So you can see David Olifeld's Pan-Arctic thermal karst map there, and we're doing, I think, a pretty good job of sampling those regions in the above domain. This colorful figure right here was in a paper that we published late last year. And so that what your eye is drawn to, that rainbow image there, is actually a subsurface geophysical result of the permafrost beneath that hotspot that we detected at Big Trail Lake, which is about a 10-minute drive from here. Essentially, we're seeing these kind of characteristic thermal karst features, that being the thermal karst undercutting, where the colors represent sort of a change in freeze and thaw state. And when you see this sort of dipping towards the land, it's an indication that the permafrost there is in a very fragile situation where the pond or the lake is really pumping a lot of heat into those surrounding ice wedges. And you can see that manifested on the surface as the classical drunken trees and thermal erosional features of literally the landscape is just collapsing into this pond. The bars on the right are sort of a preliminary qualitative finding that we actually are seeing higher hotspot numbers in these areas predicted by David Olifeld's mapping product to have the highest rates of lake or wetland type thermal karst. So we really want to try to dig into that work in the future. I want to focus a little bit here on also a brand new thing that we're looking at. So we're looking at historical fires in the Yukon-Kuskokwim Delta and counting hotspots in the burned versus unburned areas and sort of some subsetted regions within those burn scars to determine if fires are having effect on hotspots. And what we find is a consistent result. If you focus on the red bars first, which represent the burned area, are consistently higher than unburned areas in terms of hotspot counts. And then if you subcategorize the fire perimeters, we really think that signal is being dominated by where the fire edges or perimeters are overlapping with water features. So we don't really know why this is yet, but we're hypothesizing that there might be some kind of edge effect in these really wet zones having to do with inputs of permafrost carbon or really high dynamic change environments that are leading to these extreme methane emission hotspots. This is my last kind of exciting science slide, but this is 2 highlights on future directions that we want to take this work. So on the leftmost side here, we have methane hotspot Gaussian filter overlaid on a RGB satellite image. So that's the red blobs you see there. And then corresponding to the same area, we have from Ingmar Nitze, landscape-derived landscape change index that he's determined. And so we see some early correlations between not just areas that are predicted to have high thermal karst, but discrete features now. So we're taking kind of a quantitative leap. Instead of just looking in areas that are likely to have these features, we're now trying to quantify the quantitative relationship. And then on the far right, this is some data points that were shared with me from Natalie Tyler and Melanie Ingram's work using spaceborne SAR to identify hotspot seeps and lakes. And we think this is a really exciting complementary opportunity because we have some evidence to suggest that those well-characterized emission pathways and lakes are likely extending onto land in some regions. And those land-based hotspots are harder to observe if you don't have a system like AVERIS. And they may represent a kind of understudied flux pathway. And so, sorry, that was really fast. I think we have time for one question before we go to our next speaker. Sander.
Yeah, thanks a lot, David.
Thanks.
Really great stuff. For the fire scars, did you have some information on like the microtopography between lowlands versus uplands and like overlay it with the other layers that you already nicely have there? Or?
We haven't brought any of that ancillary data in yet. This is just kind of we just have the fire burn polygons. I think you can kind of assume that the areas near the water edges are kind of these little thin channels and gullies that occur in the area. But yeah, we're excited to dig into this, and I know we've talked about it a little bit, but
so how did you kind of map the water then? That's just from the AVERIS images?
Yes, we use a IR threshold in the methane retrieval to mask out water surfaces because we actually can't see methane over the SWIR dark water features. So it's a little bit of a coarse method, but I think it works well for aligning the methane hotspot data.
That's interesting.
Thank you.
Thank you, Clayton.
Okay.
Now we move to the third talk. Our speaker is Martha Bhaskara. Am I correct? That's good, Okay. She's from NASA JPL, and then she will present a similar topic. Go ahead. You can go there and drive the presentation.
So This I'll be talking about some work which builds off of some work which Clayton and others have done previously. So next slide. So just to give a little bit of background, and which is probably not really needed for this audience, but just real quickly, you know that methane emissions from the Arctic are critical, especially with polar amplification of global warming and thawing permafrost and so on. So it's important to account for how much of methane is coming from these regions and to understand the spatial variability of these methane hotspots as a function of various environmental drivers. This is critical not just to understand the mechanisms driving these hotspots, but also to be able to scale up and understand what's happening in the whole Pan-Arctic region and in the globe following on. So as I mentioned, this is work which builds off of work which Clayton and others have done previously. So in a work published in 2020, Clayton looked at methane hotspots in the Arctic domain and found that methane hotspots exhibit a power law, two-component power law, as a function of distance to standing water. So what this means is, so closer to water, like say 10 meters from water, the occurrence of methane hotspots is much higher, and this relationship kind of goes down as you move away from water, first steeply first, and then more gradually after that. So that's the two-component power law. And this was done for the whole Arctic domain. So we wanted to understand this a little bit more and look at how this power law changes or varies with respect to when you're looking at different geomorphological conditions. So we focused on the Mackenzie Delta in Canada. And so this is this region in Canada where we had about 30 to 35 ASNG flight lines. And we derived methane hotspots from using certain bands in the ASNG data. And we looked at the spatial distribution of these hotspots. This just gives a sense of how it looks like the brighter colors you see the higher occurrence of methane hotspots. And pretty obvious it's not uniform, but there's not really, it's hard to tell the pattern. So what we did is we differentiated the area into upland and lowland regions. So the lowland is the main delta, the Mackenzie Delta region, which is low-lying alluvial plains. And the upland is more hilly regions and more plateau regions and a lot of undulating terrain. As you can see, the vegetation is different in both of these regions. The lowlands is more wetland type vegetation. So we wanted to see how the hotspot occurrence varied across these upland and lowland regions and whether there were certain environmental drivers which could be important, specifically like changes in elevation, slope, and water table height and vegetation. So what we did is, so we, along with these methane hotspots, we used Arctic DEM data to derive to get the elevation at each point. And also using that information, we derived a variable called delta Z, which is representative of the water table height. So what delta Z is, it's a difference in elevation at a certain point and the elevation of the closest water feature. So it's kind of a proxy for water table height. And so what we see here is, this is the power law plot, the Poisson methane hotspot occurrence for lowland. That's for the upland. Those are the red dots. And this is on the x-axis, we have distance to water. On the other y-axis, we have the average delta Z at each of these distance bins. And immediately you can see how the geomorphology between upland and lowland varies. In lowland, we have a more flatter terrain. In upland, we have this a lot of change in elevation of the gradient and so on. And so some key points or key takeaways from these two charts is, in lowland, you do see this, and in lowland and upland, kind of the decline in slope, but in lowland, it's a much more gradual decline compared to upland regions. And also this point of inflection is about at 30 to 35 meters in lowland, and the corresponding delta Z average delta Z is about 1 meter. In upland, that would be between 35 to 40 meters, and the average delta Z is about 3 meters. So what does this mean? So in lowlands, so a couple of our main conclusions were, in lowlands, we have this more gradual decline in the hotspot occurrence, and which is kind of a function of the landscape. You have a more shallow water table in the region. So there's a more gradual decline in the hotspot occurrence as you move away from water bodies. However, in uplands, you have this more steeper decline, which is also a function of the region, of how the geomorphology in regions. That region is more, you have more of these hilly regions and more steep declines in elevation and so on. So the effect of these water bodies is kind of between that 35 to 40 meters, which was kind of evident from also some of the analysis we saw. And another kind of result we have from this work is, I haven't shown the figures of this, is so we looked at, similar to how we looked at delta Z, we also looked at the slope. How does this relationship, the power law curve, vary with the slope in the region? And we did find a positive relationship in both upland and lowland. And what that means is when you have an abrupt change in elevation or a increase in slope, the hotspot occurrence increase, which is what kind of we do expect in this region. But just having this quantitative analysis helped us kind of further understand this a little bit more. And we also found that, so the relationship with the slope also helped us understand what is the height of the saturated layer, which is kind of required to oxidize some of the methane, which is coming from the subsurface. That was up between 90 and 200 centimeters based on some of the analysis, which is higher from some of the previous work. But we think, this is based on this analysis and the region we're looking at, this is what we found. We also did some work looking at these relationships with vegetation, and I haven't shown those results, but if you're interested, I'd be happy to share them more. And I think that's it. Happy to take questions.
Any question or?
I have a question. This is Katie online.
Hi.
Did you measure the oxygen content of the soils, or how did you determine that?
We did not measure the oxygen content of the soil. Our main kind of soil indicator was just the water table height. That was the kind of our proxy for soil conditions.
I have one question. Are you planning to converting those hotspots concentration signal to flux, like emissions?
We've done that at Big Trail Lake because we were, there's some assumptions you have to make about air stagnation and wind speed and the size of hotspots and this and that. And so we have kind of an empirical model based off of our ground-based data from Big Trail Lake. And so we can do it with that model, but it still carries a pretty large uncertainty. And so it's at such a fine scale that it's pretty challenging, but we can put some bookends on what to expect in terms of fluxes. Yeah, but we're definitely working on developing that.
Thank you.
Thank you.
Or the next speaker is Nick Hansen. Right.
Animations. Okay.
Yeah, he's going to talk about characterizing terrestrial thermocast methane hotspots using very low frequency electromagnetic carbon flux coupling.
All right, well, hello, everyone. It's an honor to be here. And I had the perfect introduction with Clayton and Lafra's background because, yeah, we're also characterizing these ecogeomorphic transitions from upland environments to transition thermokarst to wetlands. And so we're looking at these methane emissions along these boundaries as they transition, but we're also characterizing the subsurface atop these emissions using an electromagnetic geophysical survey. And so we've already been talking a lot about Goldstream Valley, so I'll just add to it that the study area is a confluence of a larger watershed and has complex hydrology. So you can see in the background, we have Big Trail Lake, our study area. In the foreground, you see one of the many creeks and streams, El Dorado. And just to note, this is in the Gedama region, which is a ice carbon-rich substrate. Next. And so the major takeaway from theory is that the Gibbs-free energy and kinetic reactions and metabolisms that control methane production follow a functionality with temperature. And so if you have a linear temperature increase, you have a linear anaerobic methane production. And we've also noted that if the rate of that change is much faster, such with abrupt thaw, then you can lead to logarithmic increases in methane production. So we kind of use this theory to drive the geophysical theory that I'm going to tell you about. And so our approach is to couple the subsurface dynamics. So here, this nice colorful rainbow is actually the subsurface to 40 meters. And so here in the middle of the lake, you can actually see the 15-meter talus with the Pleistocene Yedemont beneath it. But what your eyes are drawn to right away are these red blobs, right? We see lateral thaw profiles underneath the margins, where Clayton Averest has detected hotspots rising. So right away, we were curious about what's happening on the edge of these margins. And at the top, you can see the methane flux from one profile across our study area that we also characterized during the cold season to try to get an understanding of what's driving this process. Next. And so from a total annual, each of these, so in panel A, we have the monthly CH4 flux from our site, and each month represents the 36 collars that we're measuring. And so you see this nice flux amplitude seasonally that we characterize from chamber plots. And then in panel B, you see a summary of these monthly emissions. And then what we did in panel C is we compared that with the much talked about Ohlefeld and Kuhn database. And so what we can infer from this is that the winter emissions are like summer emissions from other ecosystems, and that the summer emissions are much higher than these 105 prior investigations in the boreal and Arctic ecosystem. And so the high winter emissions accounted for 47% of the growing season and 77% of the annual flux, the median. And this points to deep subsurface dynamics, right? Because the active layer and the vegetation are frozen during the winter. And so this drove our hypothesis that, depth of thaw and saturation have to be controlling these emissions, i.e. the talic geometry. So we'll look at that next. And so here are all the fluxes that you saw in the previous, but ordered by magnitude. And so here you see a logarithmic chart of methane flux. And right away, we can see that there's this high tail end. And so what we found is that 90% of the annual flux trend was dominated by these hotspots, or 15% of the observations. And so what we found, these color scale, is that we find high saturated zones to be corresponding with these hotspots. Next, please. And the major result is that I just showed you the individual fluxes, but here each point represents the annual mean from each collar. So you're seeing 1 year of data per blue point. And if you then ask, well, what is the integrated resistivity or saturation at depth of 15 meters, and plot the corresponding flux magnitude, you end up with this really nice relationship showing that methane flux follows an inverse exponential relationship with depth of thaw. And we actually, from one of the most persistent hotspots in the winter, the surface derived, chamber-derived radiocarbon date of the gas was 35,000 years. And that corresponded to 14 meters of thaw. Next, please. And so the big takeaway is that the winter emissions are very important because that Kuhn et al. Database is actually, even though it's terrestrial derived carbon, it's missing November to March. And so we want to characterize these cold season emissions, which are high, because the implications are, it's a question, does the cold season emissions wipe out growing season CO2 uptake? The other thing we did was we characterized the temporality and spatial distribution of these hotspots that Clayton and Lathrop are characterizing, but through the cold season. So you see the mean was half of that with the cold with the hotspots, and that some of these hotspots are linked to deep thaw and very old carbon Yedemont age. And so yeah, we discover a physical mechanism controlling the methane emissions, which is a function of temperature, right? And saturation has a, water has a huge influence on resistivity, and water and saturation at high temperatures control the methane production. And so we can almost algebraically use methane and resistivity as a transfer function. And so the next slide. So what I hope to do moving forward.
Yeah, about 1 minute.
Oh, perfect. what I hope to do moving forward and how it really relates to the above domain is that the VLF-EM method is actually a remote sensing method. So we can do this from airborne. We can couple this with SAR, and we can start to characterize the thallic geometry, which gives rise to the methane emissions. And I hope to, start doing flights over Alaska and making these resistivity flux indexes. For example, imagine if we could assign a saturation index to each thermal karsted lake, say 20 ohm, 50 ohm, 100 ohm, and start to see if that corresponds to the actual methane emissions. Next. And so, yeah, if you want to learn more about the method, which I didn't really have time to go into, it's a little complicated. I have a poster in Murray Hall, number 48. I'm happy to discuss with you, and I just want to thank the sponsors and funding here. So thank you for your attention.
Hey, could you kindly expand a little bit on how you would use the SAR, like information from SAR?
Sure. So Melanie Ingram has done some excellent work characterizing the ebullition of lakes and with backscatter. And so if we have a flux of, say, high SAR-induced signals already indexed, we could use the VLF method, say 2 or 3 transects across the lake, either at the ground or airborne, to say, well, what was the mean saturation index at 15 meters or 20 meters? And we'd get a value and say, for example, Big Trail Lake, the mean of 200 lines there is 47 ohm. It's also one of the highest methane emitting lakes that we know of. So 47 ohm maybe translates to a high methane production, but maybe 100 ohm mean is a smaller, younger lake because it's only 5 meters deep. And so if we start building a roster, and we have a lot of that data now, then we could start assigning and plotting. Imagine a figure where we plot the average resistivity of saturation of lake thallics versus methane. It would be a really nice linkage. And so that's what I hope to do in a couple papers from now. I'm building that roster now. Great, it's a great question.
Cool, great
Cool.
presentation, Nick. I think we should move on next to Ethan Kizivad, who is joining us virtually. And he's going to discuss the importance of emergent aquatic veg on methane emissions in our domain. Take it away, Ethan.
Awesome. Thanks, Clayton. Can everyone hear me okay?
I think so.
Okay, great. So you can go to the next slide. The purpose of my talk is to look at the spatial heterogeneity in methane emissions. And again, the previous talks framed this really well. As we can see, methane emissions do not vary smoothly across the landscape, nor even across lakes. And so I'm taking these observations that have very consistently shown that emissions from lakes are larger in the shallower and vegetated areas. And these areas can also be thought kind of as wetlands. It's kind of like the boundary between what you'd call a lake and a wetland, the littoral zones of lakes. So that's the motivation of the work. Click. And so that motivates 2 questions. The first is what fraction of boreal zone lakes are covered by this emergent aquatic vegetation? And I focus on this on vegetation because it's actually observable from SAR and from airborne remote sensing. Second question, click, is how, if at all, could the methane flux upscaling estimates be impacted if we have knowledge of the breakdowns of these zones and can attribute different fluxes to them? Okay, so next slide, please. Method number 1. Sorry, this is an awkward one to dictate the slide changes to. So briefly, my methods are using the UAV SAR L-band data. So that's 5 meter pixels. And I developed a land cover classification, supervised classification using field samples. And so for every lake, I can detect whether it's a completely open water surface or whether there's emergent vegetation. And I'm able to get 3 granular classes, graminoid, shrub, and forest. And it's really mostly the former 2 that we see in lakes. Next slide, next click, please. And so secondly, once we can measure the areas of vegetation in these lakes, we've coupled them with flux measurements. And the key is to take or find measurements that are taken concurrently from the same lake from both vegetated and unvegetated areas. And so when we were in the pad, the Peace Athabasca Delta, our southernmost site, we took some of these fluxes, and I've also supplemented them with values from the literature. Next click, please. With these two measurements, the flux and the area, we can do what I've heard Clayton call a paint by numbers upscaling estimate. So we can test two scenarios, one where the whole lake is blue, and that would be just open water, and one, as shown here, where there's regions of emergent vegetation that likely emit larger rates of methane. And we can compare the difference between these two scenarios to come up with a sort of underestimation scenario. Next click, please. And finally, you might, as I mentioned, these areas could be considered wetlands, and oftentimes they might actually show up as wetlands on maps. So we want to make sure that we're not double counting, and all of these emergent lake vegetation areas are actually coming from pixels that would otherwise be attributed to lakes. And so I have to gloss over the details, but we did a correction with hydro lakes. Next slide, please. So first, the results. This first column here is an example of the L-band SAR images in a Freeman decomposition. The second column is the classification results. So of course, blue is water and shades of green are vegetation. The top two sites, Yukon Flats and the Peace Athabasca Delta, are the lowland and wetland sites, and you can see they're covered with emergent vegetation. The bottom two sides are the Canadian Shield, both north and south of the tree line. And so again, with the topography, these lakes sit in a shield landscape with much steeper margins, and therefore less shallow regions where plants can grow. Next click, please. And summing up all these classifications over the study sites, you can see we can see a little bit of multi-temporal change, limited by the number of airborne observations, but there's always more coverage of total inundation, particularly from vegetation in the early season and less in the late. And you can see that the lowland sites have this greatest coverage. And if we average it over all the sites, we get a 16% mean lake vegetation coverage. And so that answers the first question of what's a good number we can use to try and estimate these areas. Next slide, please. And then with the methane flux. So as I mentioned in the pad, we took these measurements. We weren't able to take both open water and lake emergent vegetation from both. So we supplemented that with literature data. So you can click. And we've added a number of other sites from about 20 papers where the criteria was, as I mentioned, studies that looked at both zones of the lake concurrently. Most of them broke it down based on open water and lake emergent vegetation, and a handful looked at deep versus shallow, which of course they use different definitions for deep. But regardless of how you break it up, the trend is clear that the shallow and vegetated zones are the higher emitters. Click, please. So if you take the average ratio of these two zones, it of course varies a lot depending on your data inputs, because it's a very data limited measurement to take. But over all of these sites, we find a 6 times greater emission from the vegetated sites than from open water. And if you look only at Arctic boreal regions, it's much higher, although we didn't use this number in the paper because we wanted to use as much available data as possible. So we used the lower number. Next slide, or next click. And if you then paint by the numbers and attribute these fluxes to the actual areas we measured, you find that the upscaling estimate increases by 21% with some uncertainty. So that's our best estimate of how upscaling might be underestimating emissions by not accounting for vegetated areas. Okay, so next slide. To revisit the research questions, number 1, what fraction is covered? We found that it's 16% on total. So next click, please. And greater fractions in lowland and wetland environments. And also if we have time, I have some slides showing the correlation between lake area and vegetation coverage. And as you might expect, there's greater fractional coverage for smaller lakes, but it's actually not a very strong trend, and it's very site specific. So that was a little bit surprising. Secondly, you can click again. How could the flux estimates be impacted? As I mentioned, our estimate is at 21% with some uncertainty. And this effect could also be larger if we're able to consider littoral areas, which are defined by shallowness and water clarity, shallowness being the really hard estimate to make from remote sensing. So right now we're constrained to vegetation measurements, but I'd kind of, I would posit that you could do the same thing if you had knowledge of the bathymetry of all these lakes, and you'd
And
probably
we have less than a minute, just letting you know.
Okay, and next slide, is my last slide. This work is soon to be out in JGR Biogeosciences, hopefully, and the data set is already available on the DAC. Last slide is a public service announcement for myself that I'm starting my final year, so I'm on the postdoc market. So thank you very much. I'll take any questions.
Ethan, this is Katie online. Super exciting work and much needed. I did wonder though, it seems like for that comparison of the open water to the emergent vegetation, the open water is not just a floating chamber, but there's also ebullition. So what are you doing with ebullition?
Yeah, I did. So for our work, we excluded ebullition based on the regression of the time-based measurements in the chamber. So we threw it out if there was potentially bubbles. For the literature studies, it was all over the place. I mean, I couldn't find, I had to take what I could get. So they used all pathways actually. And as we know, ebullition is often not possible in the deeper water. So yeah, and that's kind of the trend that I saw.
All right. Thank you, Ethan. I think we need to move on to Woo Sun, who will be also presenting virtually on improving constraints of climate sensitivities of photosynthesis and respiration using observations. So take it away, Woo Sun.
Thank you. I'll be switching gears to talking about CO2 now. I'm a postdoc at Carnegie Institution for Science, working with Anna Mikulak. I'm going to talk about using atmospheric CO2 observations to constrain the biome scale temperature sensitivity of ecosystem respiration over North America. This work is a collaboration with Josh Fisher and the Trevor Keenan's group. Next slide, please. So first of all, I would like to thank our funding sources and data providers. This research was funded by a NASA IDS award. Next slide, please. So I want to begin with the issue that we know that climate models disagree on how the terrestrial carbon sink will evolve in the future climate. And part of the large model disagreement comes from the fact that they cannot even simulate the present day carbon fluxes very well. And one example concerns the total ecosystem respiration over North America. The left figure shows a histogram of current model estimates. And we can see that excluding a few outliers, estimates from terrestrial biosphere models in the MISMAP and the Trinity ensemble generally vary by a factor of 2. And this uncertainty is much larger than models compared with the data-driven estimates in the FluxSum ensemble. So this large uncertainty may come from 2 major sources of model bias, among others. One is the bias in the magnitude of ecosystem respiration, and another is bias in its temperature sensitivity, which could be potentially more concerning if we are to project the current state of ecosystem respiration to a warmer climate. Next slide, please. So the motivating question for this study is that can we determine the biome scale temperature sensitivity of ecosystem respiration in the presence of model spread? For this work, we focus on North American domain, and later I will also give an overview of how we plan to apply this framework to the Arctic and the Boreal region. Next slide, please. So the way we approach the problem is to optimize the temperature sensitivity of ecosystem respiration against atmospheric CO2 observations. We adjust terrestrial biosphere model output of ecosystem respiration using a temperature function in the form of Arrhenius equation. the parameter to optimize in the equation is delta EA, which is the adjustment to the activation energy of ecosystem respiration on the bound scale. And the objective function is the mean square error between the observed biospheric CO2 signal with background values and the fossil fuel influences subtracted, and the transported CO2 signal resulting from modeled carbon fluxes. So with this approach, we can optimize the temperature sensitivity of ecosystem respiration for each model. Next slide, please. So here is the main result. We find that the optimal adjustment in the temperature sensitivity of ecosystem respiration shown on the vertical axis is correlated with each model's original temperature sensitivity derived from the model output of ecosystem respiration, shown on the horizontal axis. We can fit a nice linear relationship between them. And if we take the zero adjustment curve as the optimal value across models, shown in the green dashed line, we can obtain an ensemble optimal temperature sensitivity for the North American domain, that is 0.43 electron volt, equivalent to Q10 equals 1.9. So this temperature sensitivity, as you can see from this figure, is lower than that represented in most models, suggesting an overestimation of the temperature sensitivity of ecosystem respiration in current generation of terrestrial biosphere models. Next slide, please. So this is the last slide I'm going to show. So this means we can more robustly constrain the climate sensitivity of carbon fluxes if we can apply a top-down constraint on an ensemble of models. So following the success of this framework, we plan to apply this approach to Arctic and boreal biomes to constrain the climate sensitivity of both photosynthesis and respiration simultaneously, leveraging the rich airborne and field-based observations in the above domain. And specifically, one improvement we envision is to use multiple constraints for the synthesis, including carbon sulfide, solar-induced chlorophyll fluorescence, and near-infrared reflectance of vegetation. And in addition to temperature sensitivity, we will also be targeting sensitivities to soil moisture, photosynthetic active radiation, and CO2 for photosynthesis. So the ultimate goal is to deliver better calibrated models for more robust future projections of climate change and the carbon cycle over the Arctic and boreal region. I realize this is all about the plan, and I'm happy to discuss more detail. And I'll stop here, and thank you for your attention, and I'm happy to take questions.
Okay, we have a question here. Yeah, we have a microphone here if you project.
Okay, thanks for the talk. Just wondering, GPP also has a temperature sensitivity. So I'm wondering how it is you isolate the respiration temperature sensitivity out of the NAE signal from what could be also a GPP signal.
Yeah, so so in the current work shown on previous slides, we did not manipulate GPP per se. We sort of take the direct model output of GPP and subtract the CO2 signal resulting from GPP and only optimize the respiration part of the signal. And we actually did some tests on whether controlling GPP would influence the temperature sensitivity of ecosystem respiration. And we found that the influences are really small, mainly because if you transport the carbon fluxes into the concentration space, the signals resulting from GPP is highly correlated with that resulting from respiration. So you would really need to introduce additional constraints on GPP itself in order to constrain the temperature sensitivity of GPP. That's part of the reason we propose to use carbon sulfide and SIF and NRV to only constrain the sensitivities of GPP.
Cool. All right, thank you. Cedric, are you presenting? Oh, Young is here. Okay, excellent. We're returning to in-person presentations. Take it away, Jiyoung, talking about a new project and looking at aquatic carbon.
Nice to meet you. I'm Jiyoung Hong, a first-year PhD student at Boston University, and I am working on a project funded by NASA Carbon Cycle Science in the Sacrificial Lab. And the project is about the quantifying the lateral transfer of heterogeneous organic carbon from Boreal system to the Arctic Ocean, and also understanding of its vulnerability. So for today, we've looked at a mass balance of dissolved organic carbon for Great Slave Lake, and this will be the preliminary estimate of VOC fluxes in and out of the lake. So the Mackenzie River is a major conduit of dissolved organic carbon from the Boreal system to the Arctic Ocean, and about 50% of Mackenzie water flow transits through Great Slave Lake, where water has a residence time of about 16 years. So since the Great Slave Lake is a large lake and it has no residence time, in the lake, VOC is partly mineralized, and also it's produced in the lake. So we'll see whether Great Slave Lake is a net source or a sink of VOC. So in order to look at the VOC fluxes, we need to collect the data. We need a data for the discharge and in situ VOC concentration. So we collected discharge data of Lockhart River, Yellowknife River, Slave River, and also the discharge outflowing from the Great Slave Lake from Environment Canada, and the small rivers that doesn't have the discharge data, we used modeled discharge data from WDM, and also we collected some in situ VOC measurement data. So we used existing measurement of river and VOC concentration and water discharge to calculate and compare preliminary estimates of VOC fluxes in and out of Great Slave Lake. So to calculate the VOC fluxes, we need to get the continuous VOC concentration. So river-specific robust linear relationship are used to make crude estimate of VOC concentration from water discharge, and it has some predictability, and we can see some of the river has high concentration and some river has low concentration. So using the derived VOC concentration data, we calculated time series of VOC fluxes. So here's the VOC fluxes of Slave River and Hay River, and this is VOC fluxes out of the Great Slave Lake. So we calculated the relative proportion of different rivers for the water discharge into Great Slave Lake and VOC fluxes into the Great Slave Lake. So as we can see here, Slave River accounts for 74% of water discharge, but it only accounts for 60% for DOC fluxes. And if you look at the Hay River, and this is Hay River, and this is Little Buffalo River, and they only account for 3% and 0.4% for the water discharge, but they account for 12% and 3% for DOC fluxes. Also, you look at the precipitation, and precipitation accounts for 5% for water discharge into the Glacier Lake, but it only accounts for 1% for DOC fluxes. So finally, we roughly calculated the DOC mass balance in Grace Lake, and the DOC flux in is roughly 20% more than DOC flux is out. So it seems like Grace Lake is a net sink of DOC. But however, the estimates remain crude and need refinements. So we need a better estimate of DOC concentration. And also we need to quantify the uncertainties. So for the next step, we need to look at what's going on in the lake. So how much of the DOC inputs from tributaries is actually mineralized in Grace Lake. And also we look at how much new DOC is actually produced in Grace Lake. Yes, so this is acknowledgement that we thank to NASA Carbon Cycle Science Program and GFWP. Thank you.
Okay, I think we have time for one question.
So there were some big fires in 2014 around the lake. Do you have any data on how this has changed the discharge and the dissolved organic carbon?
So for now, we just did a rough estimation, so we haven't did it yet, but we're.
Do you have like annual data for all these different tributaries, or?
Oh, we have the daily data.
Daily data for like since.
Oh, since 2000 to 2020.
It'd be interesting to look at that.
Yeah.
All right, very nice. Thank you. Well, we have about 15, 16 minutes left, and we have 2 more presentations, so I think we can do it. Joining us virtually, we have next we have Qing Ying, who's talking about some more methane fluxes, return to methane, and some strategies to leverage machine learning. So this will be a new interesting tool. So go ahead and take it away, Qing.
Okay. Thank you. I'm Qing, a postdoc at Earth System Science Interdisciplinary Center at University of Maryland. And for today's presentation, I want to talk about a project that has just kicked off in April. That's to leverage the machine learning and remote sensing to upscale the on-the-ground flux tower observations of the methane fluxes in the Arctic and boreal wetlands. And I want to talk about the challenges and strategies that we plan to do within this project. Next slide, please. So the motivation of this project is to develop a comprehensive framework to integrate the multiple remote sensing products and the FluxNet CH4 database, and to reduce the uncertainties in the estimation of methane fluxes in the global methane budget. So the global methane budget studies suggested the bottom-up methods estimated about 30% larger global emissions than the top-down atmospheric constraints, whereas the most important source of uncertainty attributed to the natural emissions, especially those from the wetlands. The figure on the right showing Tsunami's global methane budget paper, that the decomposition of the methane emissions by sectors. So we see 17% emission was from the fossil fuel production and use, and 28% from the agriculture and waste. 20% was from the wetland emissions. On the figure, in the figure on the bottom left, we can see that the distributions of methane hotspots by different sectors, from wetlands, fossil fuel production, agricultural waste, and biomass and burning. And they vary spatially, and there are large heterogeneity, spatial heterogeneity by different land cover types or different land uses. So therefore, one of the priorities for improving the methane budget is to map high resolution water saturated land and inundated areas and characterize the methane emitting regimes. Next slide, please. Thank you. So the research questions for this project include: how does the finer resolution remote sensing data can help improve the characterization of spatial distribution and heterogeneities of wetlands, and how to leverage machine learning algorithms for identifying regions of methane hotspots? What are the challenges to scaling up the time series of flux tower methane with remote sensing products and machine learning strategies? And how do the scale up would contribute to the estimates of regional and even global methane budgets compared to the process-based model or top-down inversions? So on the right panel, we show a map from John's paper in 2021, showing the existing wetland products have focused on the methane hotspots, where extent of those products diverging a lot and resulted in the uncertainties. On the figure on the bottom left shows the comparison of wetland areas between existing wetland products. The left panel is comparing the dynamic inundations, and the shaded area shows the annual mean max area and annual mean minimum area.
Jane, you have about 1 minute.
Oh, okay. Yeah, I'm gonna be quick. And the right is comparing the static inventories wetland data sets. So one of the advantages to go for wetland characterization at a finer resolution is to reduce the uncertainties of methane emissions when we scale up from flux tower observations, which normally measure the methane fluxes at 100 meter to 1 kilometer footprint. Next, please. So one of the data we're going to use is the Landsat Analysis Ready data. that data set has been used to monitor global forest disturbances, cropland change, and open surface water at 30 meters spatial resolution, providing great potential for monitoring vegetation dynamics and the water inundation dynamics in high resolution wetland mapping. Next slide, please. So to improve the understanding of the Arctic wetland methane budgets, we propose a fully integrated framework to characterize the spatial and temporal variabilities of the Arctic methane fluxes. And firstly, we develop a strategy to integrate existing wetland products and train spectral features obtained from the Landsat ARD to build a model for mapping the wetlands in the Arctic. Existing wetland distributions, such as the bold Cathay peatlands and hydro lakes, those have delineated shapefiles with attributes of the wetland types, composition of vegetations, but it lacks spatial details in vegetation abundance. So the frequency, so we're gonna incorporate those data for the characterization, and the frequency of water presence will be calculated from PECO's global surface water product, and inundation gradients will also be modeled by incorporating the soil moisture active passive satellites map and products, the soil moisture products and freeze and thaw state products. Next, please.
Jing, I'm sorry, but can you try to accelerate, because we're running out of time and we have one more speaker.
Sorry, yeah, this is my last slide. It's just showing a case study. We incorporate the whole framework to upscaling the flux tower observations to regional methane fluxes in South Florida. Yeah, I'm gonna conclude my presentation here. Thank you.
Very interesting. And if anyone has a question on this kind of state-of-the-art approach, please reach out to Ching. Unfortunately, we have to move on.
Can I make a quick announcement related to the presentation?
Yeah, super fast.
Okay, so this is part of a big Pan-Arctic upscaling project that we just started. That's going to be 2 years. It's joining up with King, Ben Poulter, and Herbert Woodwell and others. So if you'd like to be a part of that, right now we're in the planning stages, getting ready for collecting all the methane data from equipment towers, and then the next stage is thinking about how we want to start upscaling building those models. So if you'd like to be a part of that, let me know. And then also we're starting to think about having a workshop sometime this fall or early winter to discuss upscaling issues related to methane. So again, if you want to be a part of that, let me know.
All right, thanks, Jenny. Okay, so quickly, let's get into our last presentation of the session, which will be given by Lei Hu, talking about the seasonal amplitudes of CO2 observations in high latitudes.
Thank you, Clayton. Okay, I'll drive the presentation. So atmospheric CO2 seasonal cycle amplitude have been increasing, especially in the Arctic. The cost for this feature is a topic of great debate. So here I'm going to show you new observational evidence that suggesting the increasing seasonal cycle amplitude in the Arctic is proportional to atmospheric CO2 concentration. Okay, here we go. So here we first updated the seasonal cycle amplitude at calculation at Barrow and Mauna Noa through 2021. And you can see over the past 5 decades, the trend of amplitude changing at Barrow is more than twice larger than what's observed in Mauna Noa. However, if we normalize the trends by annual CO2 mole fractions observed at both sites, you can see that trend is mostly disappeared. We also looked at a few other independent observational data sets that's confirming similar message. The first data set we explore is the marine boundary layer reference, which is a NOAA data product constructed from 43 CO2 marine boundary layer measurements across globally. So from this product, we calculated seasonal cycle amplitude as a function of latitude, showing on the top right, and for the first 4 years. So you can see that the seasonal cycle amplitude and the amplitude increase is the largest in the Arctic. So however, if we do similar analysis, normalize that amplitude by atmospheric CO2 mole fractions, you can see the enhancement in the amplitude increase in the Arctic disappears. So here, besides that product, we also looked at 11 long-term Arctic sites measuring CO2 besides Barrow. So we have 11 sites, not just Barrow. So here we get similar message. When we look, when we normalize the amplitude by annual CO2 mole fractions measured by individual stations, the trend disappears. Lastly, besides CO2, we also look at delta 13 CO2 and COS measurements made in the Arctic. Delta 13 CO2 measures a ratio between 13C versus 12C. The reason they have seasonal cycle is because the plant's preference on lighter isotope during photosynthesis. So the fact that this seasonal cycle amplitude has been constant over time indicate that if the isotopic discrimination rate remain constant, it's very likely the seasonal cycle amplitude of CO related to NEE flux is proportional to atmospheric CO2 concentration. And on the right, that shows the COS. COS is a very good proxy for GPP, especially works very well in the Arctic. So it shows the COS, seasonal cycle amplitude, normalized by COS concentration. So you can, as you see, the constant trend indicate that the seasonal cycle change of the GPP is also likely proportional to atmospheric CO2 concentration. So all those long-term observations suggesting CO2 fertilization is a dominant driver for Arctic CO2 seasonal cycle amplitude. If true, why there is a gradient in latitudinal gradient in the increase of the seasonal cycle amplitude? So to answer that question, we conducted carbon tracker simulation where we can transport flux by different sector by 23 different transcon regions. So we can isolate the long terrestrial flux inference on the seasonal cycle amplitude. So here, first quickly show you that we can compare the simulated seasonal cycle amplitude versus observed amplitude. And you can see that they agree very well. And also we can simulate the seasonal cycle amplitude change very well using a carbon tracker. So here, the last results I'm going to show you is that, so from that simulation, we identified the top 5 regions that contribute to the seasonal cycle amplitude observed at Barrow and Mauna Noa. And coincidentally, they are the same 5 regions that contribute to the largest contribution to the seasonal cycle, which were listed on the right there. So I think this explains why we saw the gradient in the increase of the seasonal cycle, as well as the gradient in the amplitude themselves, because those fluxes from the boreal and the temperate ecosystems, they were diluted more when they transported to Mauna Noa compared to Barrow. And we think that's the primary cause. And finally, those are the main primary findings we find so far. I know it's a lot to digest, but we are eager to hear comments and suggestions for this analysis. Thank you.
We are officially in the break time, but if you have a burning question for Lei, please fire away.
Go back one slide. So when people explain like the ratio of the boreal versus the temperate and because once you have done your atmospheric transport, like it's already everything is getting mixed, right?
Mm-hmm.
So how do you track?
Yeah, we actually transport, like we divide the globe into like 23 transcon regions. Right. So in each region we can keep tracking of how much that flux is converting to more fractions, I layered, I borrow and.
Oh, it's just like a fact tracer.
Yeah, yeah, so that's what actually shown here. So you can actually see the contribution in each region indicated this is ppm space. So that's why using this, we can calculate how much fraction they contribute to the staging cycle amplitude by regions.
Okay, yes, if people want to head out, our next program starts in 10 minutes, but feel free if you want to hear Alex's question to stick around.
Thank you.
You said something about the EPP season cycle amplitude being proportional to the circumference. Is that right?
Yeah.